Without the assumption of referential transparency in our language, bindings can no longer be considered as just name-value associations. We now need to consider them as name-location associations, where location here refers to a memory location. Now, the substitution model failed to represent these mutable bindings in this new paradigm, so in this video, we'll discuss a new model known as contour diagrams, or sometimes referred to as the environment model. But first, let's discuss some definitions. So first off, a binding, otherwise known as a variable, is an association between a name and a value, as before, but now it's mutable, so that value may change over time. A frame is a data structure that's used to keep track of any existing bindings and their current values, i.e. it's essentially a list or a table of bindings. A single frame corresponds to a single scope, or also an activation record, something like what we can see in the slides here. And it's worth pointing out that each frame also contains a pointer to its enclosing frame. This would be the lexically enclosing block, assuming lexical scoping. So if we have one frame, it refers to its parent frame, which refers to its parent frame. This creates a sequence of frames known as an environment. So an environment is a list or a sequence of frames, much like we can see in the image here. For example, we have the local frame, and then that refers to its enclosing frame and to its enclosing frame, ultimately up to the global frame, and then off to the primitive frame for things like addition and multiplication. So the environment provides a context for evaluating some sort of expression. So expressions always need to be evaluated in the context of some environment, where the local environment is the sequence of all the existing bindings relative to the current point of evaluation. So for example, if I said plus x1, the value of that expression depends entirely on where I'm asking that question. If I'm asking that in a scope where x has the value 2, then plus x1 would be 3. But if I'm asking that in a different place where x has a value of 100, then it'd be 101. So the value of expressions is dependent on their context or their environment. Specifically when we're dealing with variables, because the value of a variable requires a lookup of that symbol. All right. Next definition is for bound variables. So a bound variable is a name for which a binding exists in the current environment. Similarly, an unbound variable is a name for which a binding does not exist in the current environment. And free variables are variables which are unbound in the current frame, but are bound in a parent frame. That is to say, they do exist in the environment. They're somewhere in that sequence, but they're not in that first frame. They're not in the local environment, or the local frame. So essentially, free variables are still non-local variables, but now we're discussing them relative to the tables that are storing them. With that in mind, let's discuss the contour model. So the contour model is a graphical cell-based model of the record of execution of some algorithm. So the process is modeled as a series of diagrams or snapshots that evolve through time. It's not going to have a picture there yet, but we'll get to one in a second. So each one of these snapshots illustrates the nested structure of the algorithm's environment. So the contour model is primarily representing the environment in which execution or expressions are being evaluated. So in short, the contour model is tracking the nesting of environments and the bindings within them as the program runs, but is doing so as a series of still frame snapshots. Now, the contour model was originally designed for ALGOL, but it's designed in a general enough way to apply to any block-structured language, though as an aside, if you're following along in the course textbook, the SICP, that uses a different model that represents the same sort of environment idea, but does so in a different way. We won't be covering those models in that class, so if you are following along closely with the textbook, you should switch over to the lecture notes for this chapter. So let's get to the model. So the model consists of a series of contours, or essentially a section of contours, where each contour corresponds to a single scope. Okay, so each one of these contours, or boxes if you want to call them that, has a single frame inside them which stores all of the local variable bindings. And then the contours themselves are nested within each other throughout the model as they are in the system. So they represent the nesting of scopes within the actual environment process. Additionally, the contour model will track the current line of execution for each contour and keep track of a return pointer so that when that contour finally is complete, we know where the process will return after that. So There's a few things that are not represented in this model, so essentially anything that's not stored in a variable. So if I just said +1, 2, for example, I'd get the value 3 out of the REPL, but it wouldn't actually be stored, so it would never be represented in the environment or the environment model. Similarly, if I created a function and immediately applied it, it would create an empty contour and then just disappear. So it would create a contour for that environment or for that local scope, but then that contour would disappear. So the overall structure would be unaffected. Also, not in the model is source code. So typically speaking, when we're dealing with these models, we'll have a source code along the side to keep track of where in the process or where in the program we currently are, but that's not typically written into the model itself. Okay. So when you are doing your first contour diagram, I recommend going through these notes here, the how to draw a contour diagram. But for this lecture, I'm actually just going to start with the video, or with an example here, because it covers pretty much all the same notes anyways. So we start with a simple piece of code. So 4 lines of code here: define b to be 5, define the square to be times some value by itself, and then finally define result to be the square of b. So if we want to draw a contour diagram, first things first, we have to start with the initial environment. So the initial environments, plural, are 2 different environments. We have the primitive environment, which is the environment provided by the language itself. This contains all the bindings for things like plus and minus and all the special forms, define, and what have you. Inside that primitive environment then is the global environment, and this is the user environment as it's called sometimes. It's the first environment allowed to be mutated by the user through, for example, creating define statements. So oftentimes both the primitive and the user or the global environment will be merged conceptually into a single contour. In this diagram I've represented them explicitly as 2 separate contours, but we don't really represent what's in the primitive environment because we don't have access to the source code anyways, so it'd be a bit of a mess to write all that down. So what you'll see in all of the other examples after this first one is that I've merged these first 2 environments, these initial environments, into one big global environment overall. It is technically 2 different things, so I want to explicitly express them as 2 separate things here, but in the future, scroll down here, you can see, generally speaking, just one outside called the global environment. Okay, so once we have the initial environment, then we're ready to start walking through the code. So a few things to point out here. On line 1 in our code, we bind the variable b to the current global frame. So we have b has the value 5 within the current frame. So each one of these contours, these borders here, contains a frame which corresponds to one of these variable binding tables. And since we defined b to be 5 in the global scope, we create a frame that has b bound to the value 5. So this just shows the current variables within this scope. And down at the bottom here we have what's known as the line pointer. This keeps track of the current line of execution. You can also call it the execution pointer. So if we're on line 1, we've just defined b, so that's done. We're now at the beginning of line 2, so pi equals 2 just tells us that we're ready to start line 2. So this is a snapshot of the process, essentially here where my cursor is, just before defining square to be what it is. Okay. Anything else I have to say there? No. Okay. So on to the next one. On line 2, we say define square to be some function that has a parameter num and a body times num. So for on line 2, we create a binding in the global scope for the symbol square to be bound to a function. Now, when we bind functions, the value that we put in here, because we don't want to write the entire function in there, it'd be a bit of a pain, is just the symbol for lambda, and then the line number on which that lambda was created. That means we can go to that line number, see where that function was created, and know that the symbol square is referring to that function. Okay, so this essentially gives us all the information we need to know because the text of the function or the lambda itself has the list of all the parameter symbols as well as all the expressions in the body. So if we go to line 2, we can see pretty much what that function is all about. Now, in addition to storing a binding between the name and the lambda, or the parameters and body of the function, we also need to know the reference pointer for that function. This will become sort of difficult and important later on, but for now it's simple and somewhat useless. So for now, just create a pointer, essentially an arrow, to the scope in which that binding was created. So since this binding was created in the global scope, so the define actually occurred in the global scope, this pointer points to the global scope. For now, that will pretty much always be the same scope as the frame later on in future examples we'll change that and it'll become very important. Okay. So again, this is because when we create a function is defined as a closure. Remember, a closure is a pair of pointers, one pointer to the text or the function itself. So that would be this lambda 2 here. This refers to essentially the parameter list and the list of expressions in the body, all the information we need to execute the function. That's the first pointer. And the second pointer in the closure is the pointer to the parent scope. That's essentially where that scope is created, or where we'll find the free variables of that function when it runs. So in this case, if we run this square function, if there were any free variables, we'd be getting them out of the global scope as the enclosing lexical block. So a pointer to the code itself, and then a pointer to the parent environment. All right. So that's the end of defining this function. So the next line that we'd be executing, since line 3 is inside the body, would be on line 4. So we have pi equals 4 as the line number, just representing that we're done with line 2 and 3. We're ready to start line 4. All right, so on line 4, just in the code, it says define result to be square b. So before we can actually before we can create this binding for result, we have to figure out what is the value that we're going to bind to it. So we have to execute this function, which is to say we have to apply the function square to the value of the variable b. So two things. First, we have to find out what is the value of the variable b. So we're currently in the global scope. So if we're at our current diagram here, in the global scope, and we ask what's the value of b, well, there it is in the global scope. It's bound to 5. If we ask what's the value of square, well, there it is. It's the lambda on line 2. So we know that the value 5 goes into the lambda on line 2. We can begin to execute that. So when we apply a function to its arguments, as when we make a function call, there's a few steps that we need to deal with. So I'm going to show you the picture here, and then I'm going to walk through all the details of the things that happen. So we get a new contour for that new function. This represents essentially that new scope, or that new activation record that needs to be created for every instance of a function call. Inside that new contour, so contour here representing the border, we give it the name square prime. That's to distinguish from the first instance of the function from a second instance, from a third instance. If we call this function many times, we're going to want to know which contour refers to which instance of the function. So we call the first one square prime, the next one will be square double prime, square triple prime, whatever you want. Okay. Now inside that contour, we have a binding frame for all of the parameters and arguments. So in this case, the function was square of num and was given the value 5. So we have a binding for the parameter num to the argument value 5. If we had other parameters and other arguments, they would also appear here. So we have a contour representing this new scope. That new scope has bindings for all the parameters and arguments. And then we're pretty much ready to execute the function. So when we execute the function, we're going to be running through lines of code somewhere in our program. So just go back to our program here. The function starts on line 2, but the body of the functions technically starts on line 3. So when we're running this code, we're going to be starting from the beginning of line 3. So if we go back to the contour for square, we can see it has pi equals 3 inside the contour, representing the fact that if we run this program, if we run this function, we'll be starting on line 3, and that line 3 just says multiply these two things together. And then when we're done, we want to keep track of where we return that value to. So this red dashed line here illustrates that when square is done on line 3, or whatever the last line of square will be, it will return back to where it was called on line 4. Let's go back to our code here. We have square b was called on line 4, so we jump up to line 3, do all the work, and when it's done, it will return the value of b times b into this space here. Okay, and that's what this drawing says. So we call the function, create a new contour for that function, create a frame in that contour. Every contour has a frame. We don't represent it in the primitive frame because, again, it'd be exhaustive, but every contour technically has a frame representing all of the bindings within that scope. Importantly, we created square inside the binding for the inside the contour for the global scope, because if there were any free variables in square, we'd want to look them up in the enclosing scope. We'll see examples of that, so we'll come back to that point later on. Right, so we create a contour, we give it a name, we give it a binding frame, and we give it a line number for the line of the body of that function. And then when we're done, we have a return pointer that tells us where that function was called. All right, so once we've done that, we now evaluate the body of the function inside this new scope. So the body of square gets evaluated as though we're standing inside this box here. So when it says times num, we say, well, what's the value of num? And it's right here, bound to the value 5. Similarly, if we go looking for the value of times, we don't find it locally, go into the enclosing scope, into the enclosing scope. Eventually we find it in primitive, and then we know that times means multiplication. Or asterisk means multiplication. All right, return pointer shows where to exit. I think that's pretty much all for that step. Okay, so then we execute the body of square. That says 5 times 5, which gives us 25, and that value returns back to line 4. So this activation record is essentially done. And notice none of those steps appear at all. Let's go back to the body of to our function here, and we can see why. This value here gets computed and returned. It's never bound to a variable in this scope. So it doesn't really appear in our model because the model is just representing the environment of execution, not the executions themselves. So because num times num doesn't get stored in, let's say, a result variable inside this function, it just does the work and then returns it. So what happens next is this contour disappears. It gets garbage collected because it's done working. And the value that it computed gets returned to line 4, and we continue on where we left off. Where we left off says define result to be whatever comes out of square. So defining a variable just means creating a new binding in the current frame, which is the global frame again. So the next picture here says collapse all of this, return 25 back to line 4, and it says create a new binding for 25 to the name result. And then it says pi equals 5. Notice our code only has 4 lines, so if we're on line 5 in 4 lines of code, then we must be done. All right. So that is an example of the contour model. So for each different scope that we construct, we create a new contour, add a frame of bindings into that contour, and then continue on the process as we already know how those processes go. It's just a way of keeping track of the environment as we're doing it. Okay, so the best way to learn about these, how to do these contour models is to just do a lot of them. So let's do some more practice here. Let's to here. So another piece of code here, sum of squares example that you might remember from one of the first lectures of the course. So we define a function square of x that's just times xx. Assume I included a proper number of brackets there. And another function, SOS, which stands for sum of squares between x and y, which says calculate the square of x, the square of y, and then sum them together. And then finally define the result as calling sum of squares with the values 3 and 4. So pretty straightforward function. So let's walk through the contour model of this. So as I mentioned before, we're going to collapse the two initial environments, the primitive environment and the user environment, down into one global environment. And we'll assume all the primitive bindings exist, but we're not going to represent them in the model because that would be exhaustive. But what we'll do instead is just represent a fresh initial environment here and keep track of all the bindings. So we have a scope for the global environment. Currently no extra bindings because we're at the beginning of line 1, so we haven't actually done any code. So let's walk through it. So on line 1 it says define square of x to be times xx, assuming another bracket. So that creates a binding between the symbol square and the function that can do squaring. So that binding looks something like this. So the name square, it's the lambda on line 1, because that's where this define was created. And we have a pointer to the global environment, because again, that's where this define occurred. So the parent environment for this square function is the global environment. All right, so that's the end of line 1. We're at the beginning of line 2, and line 2 says pretty much the same thing, but for sum of squares. So we get another binding. Sum of squares is the lambda on line 2. That was also created in the global environment. Notice it doesn't matter what the body of those functions are yet, because we haven't actually executed them. We've just so far created the bindings between the names of those functions and the relevant details of those functions. All right, so on line 3 it says define result to be sum of squares 3, 4. So before we can create this binding, we need to know the value, so evaluating the sub-expressions. And that says apply sum of squares to 3 and 4. So when we apply a function, we create a new contour, a new scope for the body of that function, where the parameters x and y are bound to the arguments 3 and 4. So on the next line, we get a new scope, sum of squares prime, where x and y are bound to the values 3 and 4. And if we're executing the body of this function, we're starting on line 2, because that's the entire function here. Okay, and then we have a return pointer that says when we're done with this scope, that will return back to line 3, where this function call was made. All right, so on line 2 in sum of squares, it says plus square x and square y. Well, it has to figure out all the values, so evaluating sub-expressions figures out, well, what's the value of plus? If we're inside sum of squares here, there's nothing local called plus, so go to the enclosing scope. That's the user environment. We go to the enclosing scope from that, the primitive environment, and sure enough, this cross means addition. Great. The next sub-expression is square of x. So that's a function application, so we have to walk through the process of applying that function, where x in this case has the value 3, and square in this case, not found locally, we go to the enclosing scope. It's the lambda on line 1 defined in this global scope. So because this was defined in the global scope, when we create the contour for this, we do so in the global scope. Notice we didn't do that inside sum of squares. It's an important distinction. Again, we'll discuss this a bit more once we start talking about some tricky scope examples. Okay, so the contour for square x, where x has the value 3, so the body of square also has the parameter name x, so we create a frame inside that contour where x is bound again to 3. The body for square is on line 1. Now, when square is done, it's going to return back to this part of the code, so the return pointer goes to the sum of squares contour, and then the return pointer from that goes back to the global scope. Okay, so we walk through the body of square here. It says times xx, where x is 3, so 3 times 3 gives us 9. Again, that's not stored in anything in the model, so it just gets returned sort of invisibly. So the square collapses, and we end up back in sum of squares. So we now have, this means addition, this has the value 9, and then we say, what's the value of this last sub-expression? To do that, we create another contour, square double prime now, to distinguish it from the first. So notice the first one disappeared because we weren't using it anymore. It can get garbage collected. But it's still a good idea to distinguish the number of times that thing has arisen so that you can keep track of how far along in the process you are. Okay, so we passed in the value of y in this case, which was 4. So inside square, the parameter x gets the value 4, and then we do the multiplication again. 4 times 4 is 16. It's on line 1. And then when that's done, that returns back to sum of squares. Now we have addition, 9, and 16. Primitive arguments, we don't bother with the contours for those because we don't have the expressions in the body for those, so we can assume those happen essentially atomically. If I say plus 9 and 16, then we should get 25 as our answer. So square double prime returns to here, so that disappears, and then the addition happens here, and that returns 25 back to where it was called. So sum of squares 3, 4 becomes 25, and we can finish line 3 to say define result to be 25. Okay, then we change our pointer to say line pointer is on 4, so previously it was on 3, waiting for that result, but as soon as that line's done, it's ready for the next line, but there aren't any, so the whole process is done. Okay, any other notes I want to make about that one? Nope. Okay, so next is just another example, sort of nonsense example here. This one you might recall a similar example early on from previous video talking about the difference between bind and set, or between define and set. So the code itself creates two variables, x and y, and then two functions, assign eg and bind eg. And then it creates two variables again, b and a, as the result of calling those two functions. So we kind of already know the results of this. It's slightly different numbers from the previous example. But we've already seen what happens here, the difference between assign and binding. But let's take a look at how that affects the environment. So we start with our initial environment. We're on line 1. We have no bindings. So on line 1, it says define x to be 3. So we create a binding for x to the value 3. And we're on to line 2. On line 2, it says define y to be 3. So the same sort of thing. We create another binding for a new value. New name. Line 3 then says create a binding for this function. Now this function doesn't have any parameters, but it still works the same way. It's still a closure between a reference to the empty parameter list and the list of expressions. Okay, so if we create that, we get the symbol assign eg bound to the lambda on line 3. Now this lambda actually, or this function, now spans lines 3, 4, and 5. So if you're not sure which value to put in here, just put the one where the word define, or if you're using a lambda, where the word lambda appears. Okay, so in this case, define happens on line 3. The function signature is on line 3, so the lambda is on line 3. It starts on line 3. And again, this was created in the global scope, so we have a pointer to the global scope. Okay. Now notice because this function spans lines 3, 4, and 5, if we've completed this binding and nothing else, then we're at the beginning of line 6. So our pointer here says line 6. We don't go to lines 4 and 5 because those are inside the function. On line 6, a similar sort of thing happens. We create a binding between this symbol and a function. So bind eg is the lambda on line 6. also declared in the global scope. Okay, and that jumps us down to line 9. Now on line 9 it says define b to be the result of calling this function bind.eg. So let's walk through what happens if we call bind.eg. So bind.eg uses a define instead of a set. So walking through piece by piece here, we call this function bind.eg, so we create a new contour for it. Now when you're creating a new contour, you pretty much always create a frame. However, in this case, there's nothing in that frame. So if you want to be explicitly correct, what you could do is put an empty box here. Whoops. What you could do is put an empty box here to represent that there is a frame there with no values in it, or you can just leave it blank to say there's no values to represent, or no bindings to represent. All right, so we have a contour for our new scope, but there's no arguments to bind to parameters. So we have essentially this: the contour, the current line number, because the beginning of this function is on line 7, and then a return pointer to say when we're done, return a value to line 9, where it was called. Okay, so line 7 says define x to be plus y 100. And I've again missed some brackets, so assume there's a proper number of brackets there. I should start running this code instead of just creating it in PowerPoint. Right, so if we have the correct number of brackets here, if we said define x to be y plus 100, if we're inside this scope here, and I said add 100 to y, well, what's the value for y? There's no local variable y, so we go looking into the enclosing scope, and sure enough, there's a variable y with the value 3. Similarly with plus, we don't find that locally, we don't find that globally, but we find that in the primitive scope. So we can say add 3 to the integer 100, and we get 103. Now, because we did bind that to a variable, that does get represented in our model. So line 7 says do all that addition and construct a binding between the symbol x and the result of that addition. Now we're at the beginning of line 8, ready to essentially return the value of x. So on line 8 it says just the value of x, which doesn't really do much, and then it returns that value since it's the last value in the entire function. So that value is what gets returned as the value of bind.eg, which is then bound to the symbol b. So if we return from here to line 9, we'll create a binding for the symbol b, and then continue on. So b gets bound to the value that gets returned, and now we're at the beginning of line 10. Line 10, a similar sort of thing happens. We create a new scope for assign eg, so we get a new contour. Again, it doesn't have any arguments, so there's an empty binding frame. The body of that function starts on line 4. Now on line 4 it says set x to be plus y 100. Again, we have to do all the lookups to figure out what plus y 100 is, but we've already seen it equals 103. And it follows the same steps, so it doesn't find it locally, finds the same global y to be 3. And then it says set x to be that 103. Now again, it doesn't find a local x inside this function, so it goes to the enclosing scope and sets this one. So if we take the next step, notice there's no new binding created inside this scope, but the existing binding gets mutated. All right, and then again, it returns the value of x. So to return the value of x, it has to look up that value, doesn't find it locally, finds this 103, and then returns that. So a gets bound to 103 in the same way that b did, but along the way, we also had the side effect of mutating that global variable. So a key difference between define and set is that set has these side effects, or side effect programming mentality. All right, so that's it for that example. It's weird getting through these whole examples without pausing to ask for questions, but again, if these in particular can be quite confusing, so if you do have any troubles with this, again, stop by office hours or post questions in the CU Learn forum, and we'll get to that. But let's go on to another example. So the next example, we have 4 lines of code, pretty similar, but a little bit trickier. Shows one other thing here that I wanted to illustrate. So line 1 just says define a new variable, line 2 define new variable, and then line 3 says define z to be a lambda, which means we're not defining a primitive variable, we're defining a function, which again is first class still, but z is bound to a lambda, and then finally we run that lambda. So let's walk through it. So we start with our initial environment on line 1. Line 1 it says define x to be 3, so we get a binding from x to 3. Then we're on line 2. Line 2 says define y to be 2, so we get a binding from y to 2. Then on line 3 it says define z to be this lambda. Now it doesn't matter what the body of that lambda is, z is going to be some lambda that was constructed on line 3. So we get a binding from z to that lambda, and this lambda is going to be executed in the global scope, so the function will be created with the global scope as its parent environment. All right, that's that. So we got a binding from z to lambda on line 3 with our reference pointer there. And then on line 4, finally, we say apply z to the value 4. So z is this lambda here, which has the parameter x, which should get the value 4. So we create a new scope because we're just applying a function. Inside that scope, we'll have a frame with the binding for the parameter x to the value 4, and then we'll execute this body. So start off, we create z prime, just because that's the name we gave it. We have our frame from x to 4, and the body of this function is on line 3, starting where my cursor is. And when we're done, we'll return back to line 4, because that's where we were called from. Okay, now the body of this lambda is entirely a let here. So a let, as you might recall, is just syntactic sugar for creating another lambda, right? So let has its own scope. It creates its own local parameters and arguments here with y bound to the value 3, and it has its own scope where it does the execution of this with those bindings in effect. So what this looks like, if we want to be explicit in the environment model, is a brand new contour. Now let doesn't actually have a name, so we'll just say let prime to represent it. But inside let we have the binding y to the value 3, and then we have a, excuse me, then we have a scope for executing the body of that lambda, or the body of that let, sorry. Now the body of that let also exists on line 3, so the whole thing looks something like this. So we have inside z we have the x, inside y we have 3, and now we're on line 3 here ready to execute the plus xy step. So if we want to find out what the values of all these things are, we don't find plus locally, we keep looking into the enclosing scopes. Eventually we find plus in the primitive scope. For x we don't find it locally, so we go into the enclosing scope, which is z, and for y we do find it locally inside this let. So plus 3 and 4 should give us 7. That's going to return to here, which immediately returns from there to here. And then because nothing got represented in our, because nothing got stored in a variable, it's not going to be represented in our model. So that 7 gets returned back to here, and then the whole function ends without doing anything. If you did this in the REPL, it would display it to the user, but it's not actually part of this model. Okay. Now the reason I bring this example up is because there's a different way of representing how this nested let can look. Because the body of this entire lambda is just the let, there's no need to have this extra space here. There's no code that's ever executed that's inside the scope of the function z that's outside the scope of the let, right? There's no code that's going to ever run where my cursor is. Any code's either going to be in the global scope or inside this let, because the entire body of that lambda is a let. So a short form for representing that is to essentially collapse them together. So because this entire z is just a let, we can say, well, it's essentially we're creating one new parameter with a constant value, right? We're always going to have y bound to the value 3. So we got our parameter x bound to its argument 4, and then this local variable y bound to the value 3, and then the body, which says plus xy. So we have two contours here representing that there are in fact two scopes, but we sort of merge them together just to make the whole thing cleaner. You're free to do either way, although I feel like this second way is a lot simpler, especially if your lambda is more complicated than just a single addition. Okay, so that's that example. There's nothing else really to show because, again, the result doesn't get bound into any results or into any variables, so it doesn't get represented in our model. In fact, actually, that will be the end of this video. We'll move into more examples in the next video that involve some more tricky things like recursion and closures and all sorts of weird scope issues. So I'll see you guys in the next video.